All right, nerds. I've already said it off camera, but let me apologize for my voice quality. One of you dirty mofos got me sick. I blame and hate all of you. So anyway, we're going to go ahead and finish up Friday's lesson that we started. And that was, what were we doing? In behavior. And talking about degrees of polynomials and things like that. We finished up by saying that's not a polynomial because fractional exponent. And that's not a polynomial because negative exponent. Yada, yada, yada. And in your class, I think we even sketched out this in behavior because I thought I was going to have time to do this question. And then I realized it was going to be rushed. So we said the reason why we know the endings point opposite directions is because odd degree. And because the leading coefficient is negative, overall negative trend. So that's how we knew that's what our endings would look like. I'm going to be honest with you. This kind of question is more tedious than anything else because you're going to be writing a bunch. Now on the homework, I made these boxes wide enough so you had space to write in them. And I didn't think about that when I was making the notes. So I'm going to write out the stuff here and then just put my answer in there. Okay? What I'm going to do is plug these numbers, all of them, into this equation. And you're going to show the work like this. What? What? This shirt? No, I've been worn this shirt a billion times. You just don't like me enough to pay attention.
No, I notice every time you wear the orange shirt.
You notice orange?
There's an orange one and then there's one that says Gators.
Prisoners wear orange. That's why I wear it so often.
Yeah.
Anyway, I'm going to put this on a calculator. Boop. Be very careful about how you type it. Make sure you get it right on the first time. Because if you're using one of these scientific calculators like this, you'll never have to type it again. You can just copy, paste, and edit it. Now, if you're using the battery-operated calculator, you're going to be typing it every single time. Anyway, -1 divided by 4, parentheses, -5, close them up. Raised to the third, minus, parentheses, -5, close them up. This calculator is a square button, squared, plus 2. 8.25. We'll plot the dots later. Great. Now, we are going to write this purple statement out for every one of these numbers that's getting plugged in. But I am not going to be retyping it. I'll show you what I mean by that in just a second. I could go through the painstaking process of making sure I type it all again. But these multi-view calculators with more than one line on the screen are great because there will always be a way to scroll up and down to highlight something that you've typed before. So that is pressed up and it is now allowing me to edit this line. And everywhere it's a -5, I'm just going to type a 4 in place of the 5. Oh, okay, I'll fix that in a second. There. But notice when you type a key wherever the cursor is, it just replaces the character that used to be there. This was a 5. I covered it with a 4. And then you can just hit enter, and it'll give you your new y value, 2. And yes, I do expect you to write out all of this work on your homework because that's how I know that that's how I'm going to make it so that the people that have a habit of just copying me at least have to accidentally maybe learn something because they're going to have to write it all if they want credit. So again, go up, and where I had 4s, I put 3s because the negative sign's already there. And I hit equals. It's pretty easy, isn't it? Tedious. Tedious. Especially if you're having to retype it every single time. Go up. Change my -3s to -2s. Hit enter. Oh, hey, look at that. Y value of 0. Y value of 0 means I figured out when my graph hits the x-axis. That's always important. Found an x-intercept. Cool. All right, go up here, make these -2s, -1s. Hit enter. 1.25. Okay, now something is going to change when I do the whole go up and press enter and start editing things here. Because these are no longer going to be negative numbers. I'll need to remove the negative numbers from the statement. So when I go up, I have to actually delete the negative symbol. So hit delete and then type 0. Then hit enter and we're going to get 2. When x is 0, where am I on any graph when x is 0? That's the y-intercept. I'm on the y-axis when x is 0. This is x-axis when y is 0. So I now have an x-intercept and a y-intercept for this graph. Cool. Now, real quick, before I write this next line. In first period, at this point, I realized I goofed on a previous line. Okay? And I needed to go back up and try to retype one of these lines. But I didn't want to have to retype all of it. So I'm just showing you something. Let's say I want this to say -1 here. If I type a negative, it replaces the 0. If I type a 1, it's going to replace that set of parentheses. So how do I create the space for me to type the 1 is the question. INS is insert. Second insert 1. There. Okay? Just so you know, that's how you do that. Okay, we already had that one. While I got the purple pen in my hand, I'm just going to fill out the next line too. Let's go up. Replace the zeros with positive 1s. 0.75. Go up. Place the 1s with 2s. -4. Okay, well, again, tedious, but not difficult. If anything, all I taught you was how to use your calculator. Let's plot these dots to the best of our ability. -5, comma, a little bit more than 8. -4, comma, 2. -3, -1/4, like right there-ish. -2, 0. -1, 1.25. 0, 2. 1, comma, 0.75. And 2, comma, -4. And we know that that's what the endings look like. And if we just try to connect the dots, we're going to get something like this. Ta-da! So, easy, but tedious, maybe. Do you think you could pull that off, though? Can you handle that? Okay. Out of curiosity, do you guys remember what we call these kinds of things or these kinds of things? Bottoms of bumps and tops of bumps? Minimums and maximums. Relative minimums, relative maximums. Together they're known as extrema. And vocabulary for where a graph crosses the x-axis. Yeah, they're known as x-intercepts. Do you know what else they're called? They're called zeros and solutions. So when you have a place where your graph crosses the x-axis, your y value is 0. And that's why they're known as zeros. They're also known as solutions. They're also known as x-intercepts. And in the next chapter, we'll use a term that is relatively meaning the exact same thing called a root. Slightly different result, though. It means something slightly different. But there we go. Zeros, x-intercepts, solutions. All of those mean exactly the same thing. A place where the graph is either going through the x-axis or just sitting on the x-axis. Cool. No big deal? Vocabulary. All right. Alrighty, so it says, take a peekaboo at this graph, and then let's talk about how many real zeros it has. Not a trick question. How many real zeros does it have? You guys can shout it out. 4. It has 4 real zeros. The two endings of this graph, they both point down. They point the same direction. What does that tell me about the degree of this polynomial? If they point the same direction. It's even. Yeah. And since they both point down, what does that tell us about the leading coefficient? It's negative. Okay, so I'm going to ask you to stretch your brains just a little. It's outside of what the book wanted you to know right now, but I think that you have the ability to answer this question. If this was all you could see, what would you tell me the degree of this polynomial is? If this was all you could see, what kind of graph does that look like? Huh? A parabola. So what's its degree? 2. What if you could see that much of it? What would the degree be now? 3. So what do you think the degree is now? 4. See? Looks like a parabola, degree 2. Looks like a cubic, degree 3. So that's probably degree 4. Yes? Is that a trick you could do for any graph? You can get away with it under a special circumstance, and you don't know what that circumstance is right now. But with what we can see here, because of the way I picked this function, because I put this on Desmos, yes, it'll work perfectly. Somebody in first period asked me an incredible question at this point in time. Just waiting to see if any of you is curious about the same thing that Julian Atkins was curious about. Julian A is what I call him. He was just looking for patterns and was wondering if... No? Man, how about that? Well, I'm not going to hand it to you. Okay. Moving on. We're going to get a full analysis of this polynomial. So we're going to be using a lot of our chapter 1 knowledge when we start talking about increasing, decreasing, maximums and minimums, things like that. This is a polynomial. And I know they're not on here, but the implication is that these things have arrows on the end. The graph never stops. What is the domain of all polynomials? Come on, somebody knows. Thank you, Alyssa. Negative infinity, positive infinity, all real numbers. Boom. Just looking at the picture, what is the range of this graph? Melissa, do you want to tell me? Why not? You just told all your table mates. You whispered to them what you think it is. Why won't you tell me? 0 to infinity, but I'm going to need some symbols. On both? Ali, you said parentheses on just the infinity, so what goes on the 0 then? Why is there a bracket on that 0? Because it's including 0. Because that dot is literally sitting at y equals 0. Parentheses mean we won't get to this value. And since infinity is not a number, we'll never get there. But the graph literally happens to hit y equals 0 twice, actually. Okay. So based on the fact that the endings point the same direction, what do we know about the degree of this polynomial? Hey class, since the endings point the same direction, what do we know about the degree? It's even. Max, you had a hand up. If you had to take an educated guess on what the even degree would be, what would you think? Yeah. It's probably a 4. Could it be other things? Yes. You don't know why yet, but it could also be a 6, 8, 10, 12, 14, 16. But the point is, you know it's at least a 4. Good. And because my two endings that happen to be going the same direction are pointing up, what does that tell me about my leading coefficient? Positive. So my leading sign is a positive value. I don't know what that number is on the front. You don't need to know. The point is it's positive. Okay? What is a maximum value of this graph? Well, what is the maximum value that you're saying there? Because you said a coordinate. You said 1, 4. What is the maximum value? 4. Good. So the difference between what is a maximum and where is a maximum is x and y. So what we say is max y equals 4 at x equals 1. So it occurs at x equals 1, but the maximum value is 4. Sir, what's up? Is the space between the minimums? Oh, nope. That is coincidental. Because if you look, this is a little bit bigger than 2, and this is a little bit to the left of -2. So that span there is 5-ish. Here, the distance between the two minimums is 4, but it could have been any even number, and the same kind of picture would have occurred. But looking for patterns. That's engaging with the mathematics. That's how you know you're thinking about what you're learning. So good for you for trying to see it, but not quite. What is the minimum value of this graph? Y equals 0. And it happens actually two places. At x equals -1 and x equals 3. Oh, a y value of 0. That's literally zeros of the polynomial. They happen at x equals -1 and at x equals 3. Ta-da! And lastly, increasing, decreasing intervals. Been a while since we've done those. And if you need to remember what that means, it means if you were riding this thing like a roller coaster, always from the left. Okay? There's your speech bubble. Whee! Okay, anyway, so starting from the far left, increasing or decreasing? Lots of people. Come on, guys, talk to me. Decreasing, thank you. So when I say from the far left, what do I have to write? Negative infinity. Sorry, I chewed that up. So when you're talking about your increasing and decreasing intervals, you're saying at these x's, this is the behavior of my graph. So from the far left, we will be falling, 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 falling. When do I stop falling? At -1. Now, because -1 is a zone where we change from decreasing to increasing, we put a bracket there. Because what we're saying is at x equals -1, we are increasing and, darn it. Seeger, is that what you were going to tell me? Sorry. Clearly we're falling. That's decreasing. Otherwise, we're not saying, whee, like I said. Anyway, at x equals -1, this is where our little roller coaster guy is going to start climbing again. That's increasing. When do I stop increasing? At +1. And at +1, I begin to decrease again. Union symbol. When do I stop decreasing? Okay, 3. And then after 3, my roller coaster will be forever climbing, forever increasing. And when I say forever, I mean to the right. So what value do I write? Infinity. Let's be really clear here. That is x approaches infinity, not y. Yes, I know the graph is going up, but this is x approaching infinity. Okay? It's not a coordinate. You want to know why the first interval of increasing is from -1 to +1? That's here. That's the first time our roller coaster is climbing. And then the last time we're climbing is from 3 to infinity. That's here. Here, from the far left of the graph, we're decreasing. And then we're also decreasing between x equals 1 and x equals 3. What's the what? You tell me what the pattern for the degrees is. You don't recognize it? It's okay. Not a big deal. We'll learn it in the next chapter. Alrighty. I appreciate you, nerds. It's been a blast.